Hi guys. So our topic today is on application of derivatives, and under that we're going to be discussing increasing and decreasing functions. Right? So to start off, every equation is a graph. Every graph is an equation, right? No matter how funny the graph looks, there's always an equation to it, right? At least bits and pieces of it. Every equation can also be plotted into a graph, no matter how tricky the equation look like, okay? Right. So we are going to look into today uh, an increasing and decreasing function of uh, equation, how when an equation increases or decreases, right? So let's just draw some random graphs first and see what happens on them. So I'm just going to pick a few graphs here. I'm just going to draw some Cartesian planes out here, right? Let me draw a couple of them here too. Okay. All right, so let's say I have a very simple graph. There, this is a nice looking, quite familiar graph, right? Then we have a graph like this, then we have a graph that goes like that, and then let's pick some more graphs here. This should suffice, I guess. Right, so let's take a look at each of these graphs and understand what's happening in them. So we also know a first order derivative. Differentiation is nothing but slope. You'll realize, you know that pretty well, that differentiation of first order is nothing but slope of the graph. Because observe carefully what this means. Your dy by dx means it is nothing but delta y by delta x. And that is nothing but change in y coordinates by change in x coordinates. That's simple, right? So this is the slope of the tangent drawn at that particular point, right? And you also discussed earlier that a derivative of a function is nothing but its instantaneous value. All right, it's nothing but its instantaneous value. So we have a graph here. So let's see what happens to this graph. Um, let's just draw some tangents at these points and see what happens to them. All right. So I have a tangent drawn there. I have a tangent drawn here, and I have a tangent drawn there. Look at that. Okay. Now let's say now I number this tangent as tangent number 1, and this is tangent number 2, and this is tangent number 3. Now take a look at how the tangent number 1 goes. All right. Now, what is an increasing function? Let's understand that. An increasing function is a function in which when your domain increases, your range also increases. From the name itself, we should be able to understand what it means, right? So when your domain increases, your range also increases. So this could be an equation, something like f of x is equal to something, blah, 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 in terms of x. So if your value for x increases, and the value for f of x also increases, then we can term this as an increasing function. So generally we call it as a directly proportional equation. So when x would increase, your f of x also increases. This happens for graph number 1. That's the slope of the tangent number 1, right? So uh, whereas for tangent number 2, you observe the other way happening. So as your value for x increases, the value for f of x decreases. Okay, in our case, clearly our f of x in this case is a quadratic equation. You can see the shape being a parabola, so I should be definitely having a quadratic equation with me, right? All right, even graph number 1 and graph number 2 both are quadratic equations. The same thing happens here in this as well. So let me draw a few tangents here as well. So take a look at that there. So I draw a tangent there, I draw a tangent here, and I draw a tangent somewhere. That, I think that looks good. Yeah, that looks good. Okay, let's. I lost the other tangent, didn't I? There it is. There. Let's call it as tangent number 1 in this case, as tangent number 2, and tangent number 3. Now take a look at what happens in this graph. As the value for x increases, you notice the value for f of x decreases. Let's call it as x1. Then this value would be f of x1. And if I call this as x2, then this is f of x2. So if you observe carefully, you'll really notice that f of x2 is clearly less than f of x1. So you see what happens here? As your domain increases, your range is decreasing. This means this is a decreasing function. That means tangent number 1 is representing a decreasing function. Let's talk about tangent number 3. Okay, tangent number 3 on the other case shows the opposite. Let's take a few values of x. Let's take a value for x to be x3. Then the value corresponding, the domain corresponding to this is f of x3, right? Let's take another value for x4, and the value corresponding is f of x4. Now you clearly notice that f of x4 is greater than f of x3. Simple, right? Now it's clearly obvious that x4 is greater than x3, and f of x4 is also greater than f of x3. This clearly means that it is a decreasing function. So let me just put this graph on the side a bit, right, and make a note of what I just said. All right, now we know case number 1, we know x2 is greater than x1, but f of x2 is less than f of x1. This means the equation is a decreasing function. Take a look at the other case now. All right, let's say now we know x4 is greater than x3. Then f of x4 is greater than f of x3. Then it is an increasing function. Quite simple, right? Right, now this is what we're going to do. Right, now this is how we get to know when an equation would be increasing and when an equation would be decreasing. All right, so this is what we're going to do. Next, let's take a look at the third graph. A third graph, on the other hand, if you take a look at it, it is always increasing. It is always increasing. So let's say x1 is here, x2 is here. Now we know that x1 is less than x2, and our f of x1 is down here, whereas our f of x2 is on top there. The range is on top, right? The f of x2 is on top. So clearly we know this is an increasing function. Quite simple, right? Take a look at the fourth one here. So you'll observe here, now the graph is pointing down. So it is a decreasing function. Now we can also do this directly by finding the value of the slope. Now if you find the value of the slope value is going to be negative, right? You'll find that the slope value is going to be negative. I remind you once again, slope is nothing but the change in y coordinates by change in x coordinates. And the definition of slope is nothing but change, right? Change in y by change in x. Change is defined as the final value minus the initial value. So let's do that as well here and take a look. Okay, so we have x1, x2, then we have f of x1, then we have f of x2. Slope is change in your range by change in domain, and the definition for change is final value, that is f of x2 minus f of x1 divided by x2 minus x1. Right, simple, right? If you observe carefully more further, you notice your numerator is negative because the first term is less and the second term is more. So your numerator is negative and the denominator is definitely positive. This means your slope is also negative. All right. So we can also do that as well. Also remember, slope is nothing but tan of the angle, tan of angle of inclination. So if I know the angle of inclination here, I can simply find out tan theta and I get the slope, right? And clearly, if you notice, your theta is in the second quadrant, so tan of the value should be negative, and therefore the slope is negative. Trigonometry also tells us the same thing. So you notice that we're going about the same thing over and over again in different ways. Whether we go through trigonometry or we apply differentiation or we apply concepts of lines, we all end up to the same thing. So, right? So it's something that you already know, but now we're putting it into words. We're putting it into an equation. All right. So, few more tricks and turns here. Right. So now take a look at this equation, equation graph number 1. Now the graph number 1 says we have an increasing function here and then we have a decreasing function. So we are talking about a single equation in which a part of it is increasing and another part of it is decreasing. That means there must be somewhere between this point, halfway through, that the graph's changing its property. Now let's take a look at the third tangent drawn there. Now the slope of the third tangent is, I'll give you a few seconds to think about it. You should get it very easily. I hope you're thinking it's 0 because it is. You'll notice that this line here is parallel to the x-axis. That means the angle of inclination is 0 and tan of 0 is 0. So slope of this line is 0. Okay. Now at that particular point, okay, at this particular point, we notice that the equation is neither increasing nor a decreasing function because the slope is 0. Right? Now take a point right after it, just after it, the very next point right after it. You will notice the slope pointing down. And take a point just before it and you'll notice a slope pointing on top. So this point is actually a critical point. That means it denotes something important happening on this equation at this particular point. So our point, a value of x, a value for domain after this point is a decreasing function and a point before this is an increasing function. So therefore, we call this point along the x-axis as a critical point. Quite simple, right? Okay. Now this is where our topic is going to rely a lot on. Now it's very important you find the critical point. Now you can imagine a critical point to be any point that you have to be cautious about. For example, let's say you're walking out of the door, right? Let's say if you were to walk out of the door from where you're sitting, what would you do? You would make sure that you would not hit yourself against the wall. Often you do that sometimes, but still you'll make sure that you don't hit it. You make sure that you don't hit your feet against the door. You're going to make sure the door is open sufficiently and then you're going to walk out. So you have a certain set of critical points. You're going to open the door sufficiently large enough. You're going to walk out of the door without hitting yourself against the wall or the door, and then you're out. And also when you're walking out of the door, you're trying to close the door, you make your fingers are not there. So all these are small critical points. So any point you pay attention, you pay extra attention or something would change there, you can imagine it to be a critical point. Now same thing happens in math as well. So here a critical point is a point where an equation changes its property. Quite simple, right? Okay, so that's why it's very important that you find critical points for all the graphs that usually you will get. Okay, now let's take a look at the fifth graph here. Okay, it's become a bit clumsy, isn't it, this area? So let me just push these make this region a bit spacious. Let me make it a bit more spacious. Push this away. That looks much better. All right, so good to go. As usual, our x-axis would be the domain axis, our y-axis is the range axis. Okay, now I'm going to find the critical point out. Now it's very, very important you do so. So how do I find the critical point? So a critical point is a point on this curve where the tangent's slope is 0. I repeat, it's a point on the curve where the slope of the tangent is 0. So let's just draw a few lines. All right, there I've got a couple of lines which almost look parallel to the x-axis. I think that should suffice, and not to be so precise. Right, so I'm going to make sure this cut touches there and this touches here as well. There, all done. So now we know at these 2 points on the curve, the slope of the tangents are 0, and there are no other points like this. There are only 2 such points on this graph. So I'm going to find the value of the domain at that particular point. Okay, let me call the value for x as x1, value for this x as x2. So these 2 are my critical points. Okay, because the slope at this particular point is 0. Now observe a point on these graphs, right? Let's call these point as A and call this point as B. Okay, now take a point just before A, very close to A, but just before A. You're right. If you're thinking about applying limits, you're right. You're taking a point just before A, but very, very close to A. You'll notice the tangent pointing on top. That means your slope of the tangent is positive. And I take a point just after A, but close to A. You will notice the tangent is pointing down and the slope is negative, and that would be a decreasing function. Let's go to the next point, B. Now what happens in B? Now if I take a point just before B or anywhere, my tangent is pointing down. That means my slope is negative. Therefore my function is also negative. Take a point after B and you notice your slope is positive. Right? So it's an increasing function there. So without us doing the question numerical itself, I know my answer. So I can conclude here that this is an increasing function. Here it is where decreasing, and here it is increasing again. Quite simple, isn't it? Okay, so we're just doing this analysis on graphs now. In a small amount of time, we'll take a equation and we'll solve that equation as well. Okay, so the equation go anything, doesn't matter how the equation looks like. You will always end up coming across critical points either way. Right, now I drew a couple of graphs here, right? I just erased it as well. Let's say I take another graph like this. Take a look at this graph. Okay, quite similar again, but it shows us something else instead. So I have a line there. I have a line that goes there. I'm going to find the critical points with this graph, all right? That's pretty much got it spot on, except the first one. So let's place it at this right position. Call it there. There. All good to go. Let's mark the critical points. You will notice there are 3 critical points here. Let's call them as x1, x2, x3. Also, if you made an observation, this is a cubic equation. This is, oh, sorry, this is not a cubic equation. This is a biquadratic equation. Let me correct that. This is a biquadratic equation. This is the cubic equation. So the equation, the degree of this equation is 3 and the degree of this equation is 4. Okay, so right. So now again, let's call these points as A, B, C. So we have these 3 critical points with us, and any point before A is a decreasing function. I hope you can all see this. Any point after A and before B is an increasing function. Any point after B before C is a decreasing function, and any point after C is a increasing function. All right. Now in this case, your domain can be from minus infinity to plus infinity. All right. Now because it's a polynomial equation, so I'm going to take my domain from minus infinity to plus infinity. So I don't know what happens, how the whole shape of the graph goes, but this is pretty much how we have for now. Okay. So this is how a discussion so far looks like, right? Now, if you have a doubt here, of course, you might have a doubt, quite obvious. I won't be surprised if you don't have a doubt. So if you do have a doubt, make a note of it and keep it. During a live session, we shall discuss it. Okay, right. Now that you understood a little bit about what an increasing and decreasing function is, let's go ahead and solve a numerical and discuss how do we represent this on paper. So as you can see, I've already taken a question. I've taken a very, very easy question. I've taken a very easy question from your textbook. It's not a challenging question at all. As you can see, it's an example. So you can easily solve it by yourself. Uh, I want you to finish the exercise and let me know where the problems come across. Okay. So during our live session, we shall go ahead and solve all the doubts that you have. To show you how to represent these questions, I'm going to take an easy one. I'm going to do it. And the question here is f of x is equal to sin x plus cos x. And the question also tells us the value for x is greater than or equal to 0 and less than or equal to 2 pi. All right. It's good that this equation is given this information, even if it's not. I think it's quite obvious it's going to lie between 0 to 2 pi. If the question is not mentioned, I would have taken it from 0 to 2 pi. Okay. If it is not in case 0 to 2 pi, the question would precisely mention it is from 0 to pi or pi to 3 pi by 2 or pi to 2 pi, whatever the value is, right? So how do we solve this? Now we don't have any graph here, right? As you can see, we have no graphs with us. How do I solve this question? To solve this question, what I'm going to do is I'm going to differentiate this question. I'm going to find the slope of the tangent. Okay, slope of the tangent at any point. All right, so let's differentiate this. If I differentiate it, I get cos x minus sin x. Okay, I get cos x minus sin x. Now that I differentiated it, I've got a slope of any tangent. Okay, I've got a slope of any tangent anywhere here. So the shape of this graph, let's say we don't know. Well, I know the shape of the graph, so I'm going to draw it. All right. So let's ignore what I'm doing. Let's just say it's I wish to express it in terms of something, and the graph goes something like that. Okay, it's a bit changed. I have to change the angle instead. It's not starting exactly there. Let's assume the graph is something like this. Okay. So now on this graph that we have here, I can draw many tangents, right? There's so many tangents possible here. I can just make this diagram a bit clumsy, and I'm going to erase all these lines. Okay, I can draw so many tangents here, right? Infinite number of tangents throughout this graph. Now out of all the tangents possible, I'm going to draw only those tangents whose slope is 0. Okay, whose slope is 0. Okay, I'm not going to take any tangents further beyond it. Right? So to do that, I've differentiated the equation, so I know the general equation of the slope. Then I'm going to differentiate this equation and I'm going to equate the equation to 0. Right? I'm going to equate this equation to 0. That means I would have cos x minus sin x is equal to 0. If cos x minus sin x is equal to 0, that means cos x is equal to sin x, or in other terms, I have tan x is equal to 1. Tan x is equal to 1 means the possible values of x are, one of them is of course pi by 4, and the other one should be in your third quadrant. So the other angle should be pi plus pi by 4. 5 pi by 4. These are your two critical points. Tan x is positive, right? So tan x being positive means it can only exist in two quadrants, first or the third. In the first quadrant, I'm simply going to write it as pi by 4. In the third quadrant, I'm going to write it as pi plus pi by 4. All right, so I have my data with me so far. The question mentions that my domain is between 0 to 2 pi. I don't have to worry about what happens anywhere after this or before this. I'm going to only worry about within these two angles itself. Now, within these two angles, my critical points are pi by 4 here and 3 pi by 4 somewhere here. Now, observe these critical points. These critical points divide this region into three intervals. Interval 1, 2, and 3. Okay. Now, what I'm going to do is I'm going to create a small little table. All right. I'm going to fill this table up. Let's say I take a table here. All right. I have a table with me there. And I'm going to fill this table up with information such as, let's say I have intervals on this side. All right. And I have my f of x equations here. All right. I have my f dash of x equation here. Now, f dash of x equation is nothing but cos x minus sin x. There, I've got that done. Next, my first interval is from 0 to pi by 4. All right, 0 to pi by 4 is my first interval. Oh, 0 can be included, right? That's not a problem in the intervals. So let's include 0 and not include pi by 4. So it's just before pi by 4. Now, if I take an angle between 0 to pi by 4, you will realize that the value for cos is greater than sine. You can take a look at the tables and you'll realize that the values of cos is greater than the values of sine. That means cos x minus sine x is positive. Take any value you want. To confirm the answer, you can take any angle you want between the two. Let's take 30 degrees, right? Let's take 30 pi by 6. Put pi by 6 in and you will see cos pi by 6 minus sine pi by 6 is positive. That is root 3 by 2 minus half is root 3 minus 1 by 2, which is positive. So it should probably come up to 0.3 something. Right. Next, we have our next interval from pi by 4 to 3 pi by, oh, I made a mistake here, didn't I? It's not 3 pi by 4, it is 5 pi by 4. Right? Right? That should suffice. Right? Rectified. Moving on. So pi by 4 to 5 pi by 4. To picturize what's happening here, I think it's better to take an angle where our critical points are, right? Let's just scribble some data here. My pi by 4 line is there, and my 5 pi by 4 line is here. Okay. Now, 0 to pi by 4, we took an angle between these two, and we saw that cos x is greater than sin x. Our job is done. Now, our next data is to take an angle between pi by 4 and 5 pi by 4. You can pick any angle you want. Clearly, you can see you have an option here of pi by 2 or simply pi itself. You can take anything you want. Let's say we take pi by 2. If you do take pi by 2, you will observe cos of pi by 2 is 0 minus sin pi by 2 is 1. 0 minus 1 is negative. Therefore, the function is also negative. That means it's a decreasing function here. Okay, this is the conclusion. This is your conclusion. All right, our next interval is 5 pi by 4 to 2 pi. 2 pi is included because 0 is included, right? So 5 pi by 4. So take an angle anywhere there. So 2 pi. So let's say that you take 3 pi by 2 itself. If you do take 3 pi by 2, you will get cos of 3 pi by 2. No surprises, it's still 0 minus sine of 3 pi by 2, which is going to be 0 minus of minus 1, which is positive. Because it is positive, all right, because it is positive, it's an increasing function. From 0 to pi by 4, the graph is an increasing function. From pi by 4 to 5 pi by 4, it is a decreasing function. And from 5 pi by 4 to 2 pi, it is a increasing function. So not worrying whether how the graph looks like, the graph should look like something like this. The graph should first increase, then decrease, and then increase. All right, back again. So you see your points would be something like this, somewhere around here. So we don't have to worry about how the graph looks at all. As long as you don't have to show how the graph looks as well. As long as you can picturize it, more than enough. The graph first increases, then decreases, and then increases back again. So the graph should look something like that. Okay. This is how you do a question. This is how you represent your answer as well. Now, for the remaining questions in your exercise and examples, I want you to follow this method. All right, I want you to follow this form of representation. Also keep in mind that your domain. Now let's say I had a polynomial equation instead of a trigonometric equation. All right, if my f of x was a polynomial equation, then in the entire limit, right, I would have my domain ranging from minus infinity to plus infinity. You'd probably have about, let's say, critical point 1 here, critical point 2, and whatever, right? So if you were to have a few critical points like this, then you again have intervals created between them. So you'll have an interval in this section, then you have another interval created here. So you have a total of 1, 2, 3, and 4. You have 4 intervals here. Now with these 4 intervals, your job is to find out where it is increasing, where it is decreasing. All right. So there are a few more things to learn in this. All right. We shall do them in the live class. Okay. There are some questions which might not have a critical point at all. They're always increasing or always decreasing, called as strictly increasing and strictly decreasing functions. So we're going to look at that during a live class. All right.